Hello, John Plesga here, and I'm going to go over the Matlab function that we used in our simulation to test the different working fluids. What we ended up developing was a function that would take the low temperature in Celsius as an input, the high temperature in Celsius, the pressure in pascals, or if you didn't know that, you put saturated or just sat, and that would take the saturated values at the temperatures you set and use those. M dot, which stands for the mass flow rate in kilograms per second, and the name of the working fluid. And what it returns is the low pressure in Pascal, the high pressure in pascals, the pump work in kilowatts, the boiler work in kilowatts, the thermal efficiency of the system, and the net power of the system. What it also shows is a TS diagram, which I'll pull up here. So this is for isobutane. It shows that there's very little pump work compared to the whole system. It also shows right here that because this is over the vaporization curve, we would need a dry fluid pump for the system, which could be pricey. Good things to know if we were to further develop the prototype. This also, just knowing that the entropy curve is like this, and from a couple of research papers, this tells us that pressurizing these refrigerants, isobutane included, does not get more energy out of the system, which is helpful because it helps us save energy. Now I'm going to show the function itself. And we'll go through a live script. So first, here's the function itself. What it does here, PyVersion, this just makes sure that Python's loaded in the Matlab because we need Python to run the coolprop database. If it's not loaded, there'll be an error message. And if coolprop isn't loaded, there'll be an error message. So if we need that, we uncomment this. This will get us a coolprop. If you need Python loaded on the Matlab, you have to do it on your own. There's instructions online. And this sets the general parameters. So it just makes the temperature high and low in the Kelvin, and it sets the turbine and the pump efficiency. So this matches what we used in the DW simulation. Then this is to make the saturated values if you don't put in P2 value in pascals. And then the rest is thermodynamic equations typically used for solutions of Rankine cycles. So enthalpies, entropies, and these are all solved by using the coolprop database and Python linked with Matlab. So anytime you see this, that's using the coolprop database and Python. What it does, it takes your desired output. So for this, it's S for entropy. And our inputs were temperature at T2, the pressure at P2, and the working fluid that we wanted. And then as we go down, we do that for the different stages. So those 1, 2, 3, 4 that we showed on the graph. And as we move down, there's a couple small tweaks we make. One, just propane. I had an issue with capitalization, so we fixed that here. Also propane, its flash point is below 400, where the other graphs were set to 400. So we had to lower that for propane to get a good graph, not an error message. This is where we set the vectors, the graph. And that is the gist of our general function. Next, I'm going to show you a live script. And this is what we used to fine tune the function before we fully implemented it. This specific example is a test of one of the textbook examples that we tested against using water. And you can see the function is the same. The live script was super helpful because it allows us to break up sections and just run solo sections. And if there's any errors or discrepancies, we can find out what's going on with either the coolprop database or the code, or and just really fine tune the results. So we get something that we expect and can repeat. And so for this, here's the TS diagram for water. You'll see it's a little bit different than the one for isobutane. It's not superheated past the vaporization curve at the end here. It's a mixed steam or mixed vapor and water. And the textbook solution, I believe, was around 66%, which is right here. And if we were to see this like for the ammonia and propane curves, we knew right here that we could use a wet fluid pump. And once again, that's just good if we were to move on of prototyping or to move on testing different working fluids. Knowing whether we needed a dry or wet fluid pump could help us out in the future quite a bit, either to save money, to plan for which working fluids to use, and what is practical use in a residential environment. So that is just a quick overview of the function we developed. If you have any questions, please feel free to reach out. My contact info is available, and thank you for your time.